Good morning, students. Welcome to 12th standard physics class. Students, today's topic is on atomic and nuclear physics, unit 9. Introduction. In earlier classes, we have studied that anything which occupies space is called matter. Matter can be classified into solid, liquid, and gases. One material is not same as another. This means that the physical and chemical properties are different for different materials. When an object is divided repeatedly, the process of division could not be done beyond a certain stage in a similar way, and we end up with a small speck. This small speck was defined as an atom. So the word atom in Greek means without division or indivisible. The size of an atom is very small. For an example, the size of hydrogen atom is around 10 power minus 10 meter. An American physicist, Richard, said that if the atom becomes the size of an apple, then the apple becomes the size of the earth. Such a small entity is an atom. In this unit, we first discuss the theoretical models of atom to understand its structure. The Bohr atom models more successful than J.J. Thomson and Rutherford atom models. It explained many unsolved issues in this day and also have better understanding of chemistry. Next topic is electric discharge through gases. It consists of a long closed glass tube, inside of which a gas is pure form is filled usually. The small opening in the tube is connected to a high vacuum pump and low pressure gauge. This tube is fitted with two metallic plates known as electrode, which are connected to secondary of an induction coil. The electrode connected to positive of secondary is known as anode, and the electrode to the negative of the secondary is cathode. When the pressure reaches to around 0.01 mm of Hc, positive column disappears. At this time, a dark space is formed between anode and cathode, which is often called Crookes dark space, and the walls of the tube appear with green color. At this stage, some invisible rays released from cathode, called cathode rays, which are later found by a beam of electrons. Properties of cathode rays. Cathode rays possess energy and momentum and travel in a straight line with a high speed of the order of 10 power 7 meter per second. The direction of deflection indicates that they contain negatively charged particles. When the cathode rays are allowed to fall on matter, heat is produced. Cathode rays affect the photographic plates. When the cathode rays fall on a material of high atomic weight, X-rays are produced. Cathode rays ionize the gas through which they pass. The speed of cathode rays is up to 1/10 of the speed of light. The next topic is determination of specific charge of an electron, Thomson experiment. Thomson experiment is considered as one among the landmark experiments for birth of modern physics. In 1887, J.J. Thomson made remarkable improvement in the study of gases in discharge tube. In the presence of electric and magnetic fields, the cathode rays were deflected. By the variation of electric and magnetic field, the specific charge measured. The arrangement of J.J. Thomson's experiment is highly evacuated discharge tube is used and cathode rays produced at cathode are attracted towards anode disc A. Anode disc is provided with pinhole in order to allow only a narrow beam of cathode rays. These cathode rays are now allowed to pass through the parallel metal plates, which are maintained at a high voltage. Further, the gas discharge tube is kept in between pole pieces of magnet such that both electric and magnetic fields are acting perpendicular to each other. When the cathode rays strike the screen, they produce scintillation and hence bright spot is observed. This is achieved by rotating the screen with zinc sulfide. Determination of velocity of cathode rays. For a fixed electric field between the plates, the magnetic field is adjusted such that the cathode rays the original position O. This means that the magnitude of electric force is balanced by the magnitude of force due to magnetic field. Let E be the charge of the cathode rays. Then small e, capital E is equal to E, B velocity. So epsilon is equal to E by B. Determination of specific charge. Since the cathode rays are accelerated from cathode to anode, the potential energy of the electron beam at the cathode is converted into kinetic energy of the electron beam at the anode. Let V be the potential difference between anode and cathode. Then the potential difference is EV. Then from law of conservation of energy, EV is equal to half m epsilon squared is equal to E by m is equal to epsilon squared by 2V. So if we substitute this value, E by m is equal to 1 by 2V E squared by B squared. Deflection of charge only due to uniform electric field. When the magnetic field is turned off, the deflection is only due to electric field. The deflection in vertical direction is due to the electric force. So FE is equal to EV. Let Y be the deviation produced from original position on the screen. The initial upward velocity of cathode ray Bu is equal to 0 before entering the parallel electric plates. Then T be the time taken by the cathode rays to travel in electric field. Let L be the length of one of the plates. Then the time taken is T is equal to L by epsilon. Therefore, the deflection Y on the screen is Y directly proportional to Y dash. So Y is equal to C Y dash. Here C is proportionality constant, which it depends on the geometry of the discharge tube and substituting Y dash. Hence the deflection Y dash of cathode rays is Y dash is equal to UT plus of AT squared. Is equal to Y dash is equal to UT plus of 2 ACT squared. So of E by m E 1 by epsilon squared. Y dash is equal to 1 by 2 E by m L squared B squared by E. Therefore, the deflection Y on the screen is Y directly proportional to Y dash. Specific charge is calculated. Topic is Millikan's oil drop experiment. The apparatus consists of two horizontal circular metal plates A and B, each with diameter around 20 cm and are separated by a small distance 1.5 cm. These two parallel plates are enclosed in a chamber with glass walls. Further, plates A and B are maintained at high potential difference around 10 kW. The electric field acts vertically downwards. A small hole is made at the center of the upper plate A and an admiser is kept exactly above the hole to spray the liquid. When a fine droplet of the highly viscous non-volatile liquid is sprayed using admiser, they fall freely downward through the holes of the top plate only under the influence of gravity. Few oil drops in the chamber can acquire electric charge because of friction with air or passage of X-rays in between the parallel plates. Further, the chamber is illuminated by light which is passed horizontally and oil drop can be seen clearly using microscope placed perpendicular to the light beam. These drops can move either upwards or downward. Let m be the mass of the oil drop and q be its charge. Then the force acting on the droplet or gravitational force Fg is equal to mg. Electric force Fe is equal to QE. Buoyant force Fb. Viscous force Fv. Once the oil drop attains a terminal velocity epsilon, the net downward force acting on the oil drop is equal to the viscous force acting opposite to the direction of motion of the oil drop. From the Stokes law, the viscous force on the oil drop is Fv is equal to 6 by rho epsilon eta. From the free body diagram, Fg is equal to Fb plus F epsilon. So rho of 4 by 3 pi r cube g is equal to rho into 4 by 3 pi r cube g plus 6 pi r epsilon eta. Okay students, today's topic is over. Today's homework. Students, I have given homework. Read the questions and answers well and write 2 or 3 times in your classwork note. Thank you students. God bless you all.